We can use techniques similar to those in the previous two videos to turn not just coordinates, but whole equations into polar form if they're given in Cartesian form, or Cartesian form if they're given in polar form. So let's take an equation given in Cartesian form and convert it to polar form. I'll start by reminding us of our formulas. If we know r and theta, if a point or an equation is given in polar form, then I can find the Cartesian form simply by replacing r with the r we're given and theta with the theta we're given, and that's going to give me the x, or in the case of sine, the y, that I need to put it into that form. Equally, if I know x and y, I can plug them into this formula to give me r, and into this formula to give me theta. What happens if I'm given an equation, not just a point? Let's start with y equals 4x squared. This is an exercise, an even exercise from the back of the section. I have a way of writing y that will put this into polar form. And I have a way of writing x that will put this into polar form. So let's do those, make those conversions. Y is equal to r times the sine of theta. And x is equal to r times the cosine of theta. My x is squared, so I need to square that entire expression. If I simplify this, I get r sine theta equals 4r squared cosine squared of theta. Now, I could simplify by dividing both sides by r here, but I have to be careful. As in any algebraic exercise, if we divide by a variable, we need to make sure that that variable is not equal to 0. Notice that only the r squared gets simplified. The cosine is still squared. So I've divided by r. If r were 0, I'd run into trouble. So I'm going to say here, r cannot equal 0. Is that going to cause problems for us? Not really, because if you think about the Cartesian plane, and then we impose polar guides onto that, right? Then where is the point where theta is some angle and r is 0? That's over here on the origin or on the pole, right? We can go around to any angle and then starting at the origin, move 0 in that direction. Well, if we don't move from the origin, if we don't move from the pole, we're still at the pole. So the case where the point would be at r comma theta, where r is 0, means the point's just going to be at the origin. So it's not really, in terms of a point, that point still exists at the origin, but in terms of a graph, it's just going to be what we call a degenerate case, right? It's kind of collapsed in on itself. So continuing with this equation, ultimately in the form, let me put this up here. Coordinate or polar coordinates look like this, r comma theta. Now, I know I've said this a number of times, but conventionally the r comes first when we write the coordinate pair. I would write 2 comma pi over 2, not pi over 2 comma 2. So the r comes first in the coordinate pair, but when I'm looking for, when I'm trying to plot the point, 2 comma pi over 2, I'm going to start by going out around, pi over 2, and then looking for where is r equal to 2 on that axis, on that line. So the angle comes first, usually, when we're graphing them. And that means that the angle, in spite of the order these are written, the angle is often considered the input variable. So we want to solve this so that the equation ultimately reads r equals, and the answer is going to have theta in it. The right-hand side will have theta in it. The left-hand side will not have any thetas in it, and the right-hand side will not have any r's in it. That's ultimately the form we want this in. So we need to solve this equation for r. That means isolating r, getting it by itself. So I'm going to divide both sides, both by the 4 to get rid of that, and by the cosine squared to get rid of that. And by get rid of, I mean get rid of it on the right-hand side, isolating the r, and rewriting the left-hand side. I'm just going to get 1/4 sine of theta over cosine squared of theta. Now there are other ways to write this expression, and I'll come to that in just a minute, but this is the form we want this to be in. R equals stuff with thetas in it, not thetas on both sides or r's on both sides. I'm now going to rewrite this as the sine of theta over the cosine of theta times 1 over the cosine of theta. The reason I can do that is that cosine squared here is just cosine times cosine, and sine times 1 is sine. So I've just rewritten this fraction here as the product of two fractions. And the reason I've done that is so that I can write r equals 1/4 sine over cosine, that's tangent, and 1 over cosine, that's secant. So now I don't have any fractional expressions anymore. I just have trigonometric functions, tangent and secant. Your textbook did question number 19 in such a way that it ended up with a sine and a cosine to the fourth in a ratio. So the answer has a sine over cosine to the fourth in it. So another way to write this, your textbook might have written this way, sine theta over 4 cosine squared theta. I prefer this form, or even you might say r equals tangent theta secant theta all over 4. And your textbook seems to be leaving them in this form. They're both equivalent. So since we don't know how we're going to use this, it's just an exercise. And so the final form of the answer should be simplified within reason. I think this is a little bit less simplified than is ideal. This form would be okay. But we don't really know how we're going to use it. So unless you're given specific instructions, don't leave any fractional expressions in your answer, or I don't know. I'm not sure how else I can say that. Unless you're given explicit instructions otherwise, I would say that either of these forms, or even this form here, would be acceptable as an answer. All right, so let me see. I think I'm going to erase some of this. I think I'll just go back to this version of the problem. I just kind of want to make an additional point before we quit this video. One of the reasons we might want to do this is that I can now take this equation, plug in various values for theta, and I can graph this thing. I'm not going to spend tons of time on this because I think it's a really good exercise to do in class, but here's how we would do it. I'm going to start by making a table of values. You won't always need this, but since we're just learning this, it might be handy. A table of values where theta is my input and r is my output. So let's pick some common values of theta. 0, pi over 6, pi over 4, pi over 3, and pi over 2. Now, what happens when I plug 0 into this equation? What happens is that I get r equals 1 times the sine of theta, my theta value is going to go there, over 4 times the cosine squared of theta, my theta value is going to go there, and my theta value in this first case is 0. Okay, what is the sine of 0? Well, it's 0. So I'm going to get 0 over something, and unless that is 0 as well, it's just going to be 0. Is the denominator 0? Let's find out. What is the cosine of 0? Once we know that, we're going to square it. Well, the cosine of 0 is 1. When you square 1, you get 1. So this whole thing here has a value of 1. Multiply that by 4, and you get 4. But 0 over 4 is just 0. So my output here is 0. All right, now that I've got that first value, I'm going to erase most of this. I'm going to leave it's kind of a formula now. So I'm going to leave that in place, and I'm going to grab my the next input value I gave myself. That's pi over 6. This might take a little bit more arithmetic. What is the sine of pi over 6? That's a half. What is the cosine of pi over 6? That's the square root of 3 over 2. But now I need to square that fraction. And when you square a fraction, you just get the top squared over the bottom squared. Since I have the square root of 3 over 2, when the square root of 3 gets squared, I'm going to get 3. 2, when it's squared, gives me 4. So my output here, let me back up a little bit. This value here is 3 over 4, and then I'm going to multiply that by 4. 4 over 1 times 3 over 4 is just 3. This fraction reduces to 1 over 6. So my output value for this one is 1 over 6. My next input value is pi over 4. So I'll put that in and ask, what is the sign of pi over 4? That's the square root of 2 over 2, or 1 over the square root of 2. I think I'll write it as 1 over the square root of 2. What is the cosine of pi over 4? Well, that's also 1 over the square root of 2. But now I need to square it. So I'm going to get 1 squared over root 2 squared. And that's just 1 over 2. But I need to multiply that by 4. 4 over 2 is 2. I write that as 2 over 1. Then I get 1 over root 2 times 1 over 2, which is 1 over 2 root 2. All right, let's do pi over 3. When pi over 3 is my input value, I get, for the sine of pi over 3, I get the square root of 3 over 2. And the cosine of pi over 3, the cosine of pi over 3, that's a half. But when I square it, I get a fourth. Then I multiply it by 4. 1/4 times 4 is 1. So my answer here is just the square root of 3 over 2. And lastly, pi over 2. Now, pi over 2, the sign is 1. Sorry. This is going to give me a numerator of 1. The cosine of pi over 2 is 0. When I square 0, I get 0. When I multiply it by 4, I get 0. So I have 1 over 0. So at pi over 2, we do not have an output value. Now, why did we do all of this? We did all of this so that we can graph this function. In order to do that, I'm going to grab these coordinate pairs and plot them in order. I think I'll use blue because it's kind of the darkest pen I have here. So the points are in order 0, 0. Let's plot that one. I get that not because it's 0 in this direction and 0 in this direction, but because it's 0 from here, it's 0 radians around, and then it's out a 0 radius, right? So it lands on the pole more than it lands on the origin, right? Because we're in polar coordinates. Now these other values are going to be harder to find, 1/6, 1 over 2 root 2, root 3 over 2. So I'm going to take a minute and go figure out approximately what these are on my calculator, and I'll come back when I have those approximations. All right, here's what I get when I plug these into a calculator to get a decimal approximation. So the points that I'm going to be plotting are pi over 6, 0.17, pi over 4, 0.35, pi over 3, 0.87. Now, I'm not going to be able to be as accurate as 0.87, so I'm probably going to have to approximate that, around that, if you will, even more to about 0.9. So the next thing I want to do is look at my graph here and decide what my scale is going to be. My input values at the moment go from 0 to pi over 2. That's here around to here. So right now we're in quadrant 1. My output values go from 0 up to 0.87. That's almost 0.9. So if I let each one of these equal 1, then I'd have to get all these points in this small region here. But if I let each one of these equal, say, 0.1, 1/10, then I have 1, 2, 3, 4, 5, 6, 7, 8 of these. My largest output value is almost 0.9. So I'd need an additional circle guide around here, at least one more, and then I'd be coming, I'll do it here, I'd be coming close to, but not quite, that 9th circle. So that's getting pretty tight around here, and yet having them too small is going to be awkward as well. So I'm going to go with this. I'm going to go with a scale of each one of these is 0.2. This one here would be 0.4. 0.2, 0.4, 0.6, 0.81. So the largest value is going to be somewhere in here. It's still not ideal, but I think it's probably as close as we're going to get. Something between 0.1 and 0.2 would be like 0.15, and I think it's just going to be hard to do the arithmetic. So if each one of these is 0.2, that's 0.4, 0.6, 0.8, 1.0, all my values are going to fall, all of my points are going to fall within this circle. And in fact, at the moment, 6, 8, 10, they're all going to fall within this region here, quadrant 1. They're all going to be in here. So let's go ahead and plot those points. I already have 0, 0 on the graph. My next point is pi over 6, 1/6, or pi over 6, 0.17. So I'm going to go out to pi over 6, which is this line right here. And then the matching output value for pi over 6 is 0.17, which is about 0.2. It's a little less than 0.2. So at pi over 6, I'm going to be just under my 0.2 circle, right? It's going to be right about there. So I'll go ahead and plot that point. The next one is pi over 4 with 0.35. So I'm going to go out pi over 4. I'm going to be on this line right here. And I want to go out as far as 0.35. Well, I don't have a 0.35, but I have a 0.2 and a 0.4. 0.3 would be about there. 0.35 is going to be about here. Then I have a pi over 3 input, which is this line right here. And the output that goes with that is 0.87, which is almost 1, which is a considerable jump from this one. Let's see, I'll count out there. Pi over 3 is this line here. So from on this line, I'm going to go out 0.2, 0.4, 0.6, 0.8. This would be 1. This would be 0.9. So I'm going to be just shy of that value. Now, the trick when you're graphing a polar equation is to recognize the order that you've plotted these in and sort of track them in that order. We plotted this point first, and then this one, and then this one, and then this one, and they kind of curve. So far, this graph is going to look something like this. The thing is, we're not done with this graph. We've only graphed in the first quadrant, right? We've only gone 0 through pi over 2. We don't know what happens when theta equals anything beyond pi over 2, but less than 2 pi. So we need to do this. We need to continue this process for those other values. I think what I'm going to do now is I'll set this up so there are new values in this column, and we'll work out what the values are in this column. I'll do the arithmetic off screen to get the decimal approximation, and then we'll just plot those points. I'm going to do it one quadrant at a time, but we'll go through it a little bit more quickly this time. So there are my new input values. I'm going to erase the input values that I had in there in the previous iteration. And I'm going to put in my first set of my new input value, 2 pi over 3. And 2 pi over 3 is just the next, from pi over 2, it's the next common angle around. So if you count in pi over 6's, you get 1 pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, which is 2 pi over 3. I'm just reducing the fractions. 4 pi over 6 is 2 pi over 3. So that's how I got my next input value. The next multiple of pi over 6 around from there is 5 pi over 6. So that's where this one came from. And then 6 pi over 6. And the one I missed was this pi over 4. Pi over 4 is 1 pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and there's 3 pi over 4. So that's how I got those input values. Now, let's do some computation. What is the sine of 2 pi over 3? Well, the reference angle is pi over 3. Oh, I need a better color than that. Let's use pink. So here's my reference angle. That's pi over 3. What is the sine of pi over 3? The answer is, get the right color of pen, the answer is the square root of 3 over 2. But because I'm in quadrant 2, not quadrant 1, everything's positive in quadrant 1. But I'm in quadrant 2, so I need to check it. What's positive in quadrant 2? Let me get a different color of pen, and I'll just write this once, and then we won't have to look at it again. All students take calculus. In quadrant 2, sine is positive. Well, that's exactly what I'm looking for. It's a sine, so it stays positive. The cosine of 2 pi over 3 is the same as the cosine of pi over 3, but the cosine of pi over 3 is 1/2. So that's going to make the denominator 1/2. Then I'm going to square it, and then I'm going to multiply it by 4. But it's the cosine, right? It's a cosine, and cosine is not positive here. So I'm going to have to make that negative 1/2. Now, as it happens, it doesn't matter because I'm about to square this, right? But it's important to be able to do this mental checking as you go, because if you miss that and it's not, you don't end up squaring that value, then it's going to be off by a sign. When you square 1/2, you get 1/4. When you multiply that by 4, you get 1. So I have root 3 over 2 all over 1, and that's just root 3 over 2. I'll go get an approximation for that in a minute. Now I'm also going to do this for the other values you see here. My next one will be pi over 4. But after that, I think I'm going to skip doing them on screen. By now, you should be able to do these. 3 pi over 4 for both of these, 3 pi over 4. What is the sine of 3 pi over 4? Well, what's our reference angle? What's our reference angle? Our reference angle is pi over 4, and that's this line right here. So if that's the reference angle, then my next question is, well, what's the sine of pi over 4? The answer is, it's the square root of 2 over 2. I need to erase my previous work here. It's the square root of 2 over 2, or if you prefer, 1 over the root of 2. Okay, that's the that's the sine of pi over 4. I wanted the sine of 3 pi over 4. 3 pi over 4 is in quadrant 2. Sine is positive in quadrant 2, so it stays positive. What's the cosine of 3 pi over 4? Well, what's the cosine of pi over 4? The cosine of pi over 4 is also 1 over the square root of 2. But because it's in quadrant 2, cosine is negative here, therefore it's negative. Now I have to square that and then multiply it by 4. When you square negative 1 over root 2, you just get 1/2. When you multiply that by 4, you get 4/2, which is 2. So I have 1 over the square root of 2. Where am I going to put this? 1 over the square root of 2 divided by 2, which works out to be 2 over 1. So 1 over 2. So 1 over 2 root 2. So that's my output value for 3 pi over 4, 1 over 2 root 2. And I'll go get a decimal approximation for that in a minute. Now, hopefully that's enough for you to see what the pattern is. We have spent a considerable amount of time working out what cosines of various angles are. We did that in previous modules. So that should be relatively familiar, if not comfortable. We've also spent some time, not that long ago, learning how to plot points in polar form. So we know how, once we find these points, these are pairs, right? This is like my input and my output. That's exactly what it is. So once we know what these values are, we can use the technique we learned in the previous video to plot these points, right? Each of these is polar coordinates. These are polar coordinates, and we know how to plot points in polar coordinates. So we'll just do that. And then we trace along in between them, kind of going in order, and that's going to cause a bit of a curve to occur here. So I'm going to go ahead and do the points for the rest of quadrant 2. I'll show you what the decimal approximations are, and then we'll plot those together fairly quickly, and we'll go from there. All right, so here is my table of values for quadrant 2. These are my input values. Those are the angles that fall between pi over 2 and pi. And these are the output values I get from plugging them into this formula, or this equation, right? Now, my next point to plot is this one right here, 2 pi over 3, 0.87. 2 pi over 3 is, there's 1 pi over 3, here's 2 pi over 3. So I'm along this line right here. And I need to go out 0.87, or almost 0.9. So if I'm tracking along this line and I'm going out by 0.2, 0.4, 0.6, there's 0.8, there's 1, there's, oh, hang on, I got messed up here. 0.2, 0.4, 0.6, 0.8, this is 1, halfway between 0.8 and 1 is 0.9, And just shy of that is here. And that's in line with this other point that was at the same distance out from the pole. So we're right about there. The next one is 3 pi over 4, 0.35. Well, there's 4 pi over 4. So if I take pi over 4 back from that, I'm going to be on this line here. So I'm on this line and I want to go out 0.35. So starting here, I'm going to go out 0.2, 0.4. Well, that's already too far. Halfway between is 0.35. Halfway between this point and 0.4 is 0.35. So that point is going to be about there. And again, that's in line with this point being out about 0.35. The next one is 5 pi over 6, 0.17. We're going to call that just shy of 0.2. So I'm going to go over to 6 pi over 6, go back 1 pi over 6. That puts me on this line. And I'm going to go out from here just under 0.2. That means that point's right about there. And if I connect these points in order, I end up with something that kind of looks like this. Now, the question is, what happens between pi over 3 and pi over 2? Or what happens between pi over 2 and 2 pi over 3? Because it's really tempting, especially once you know a little bit more about polar graphs, it's really tempting to try to connect these in some way. But as it turns out, because one of my expressions is squared and the other is not, this is actually, well, I'm not sure I want to give it away. My video is already so long. What's going to happen is, I don't know if you remember, when we were approaching pi over 2 in the previous, when we were working in quadrant 1, I had pi over 2 in this position, and I just had a line there because at pi over 2, the function is undefined, right? Because at pi over 2, the cosine of pi over 2 is 0, and so we had divided by 0 here. Now, the thing is, when we graph using tables of values, all we're doing is giving ourselves some landmarks. Notice that when I graphed this region here, these were the points that I got from graphing some common values in quadrant 2. These are the values I got. I did not plot points for, here, let me do this. Here's the point I got for when theta was 2 pi over 3, and here's the point I got for when theta was 3 pi over 4. I did not plot the points in between those two values, but I could extrapolate from the fact that these 2 points were here that there would be points in between them, right? So there are going to be there are going to be points in between the point associated with pi over 3 and the point associated with pi over 2. In other words, if pi over 3 is my input and I get a value, it was 0.87, and if pi over 2 is my input and I get an output value there, which I didn't because I had the output value was 1 over 0, which was undefined. But there are angles in between here, and they're going to have values as well. And for each one of these angles, starting with 0, we did pi over 6, we did pi over 4, we did pi over 3. We could do the same for these, and these values would keep getting bigger. The output values would keep getting bigger. And so ultimately, our graph would look something notice how each one of the points on this curve has a larger angle value and a bigger radius than each of the previous ones. So for example, this is the point associated with pi over 3. The next angle guide line over is here, and that point is farther out. It's got a bigger radius. The next point, the next angle guide line over is here, and in fact, its point is so far out that it's off the chart. So this is what happens, and then as you approach pi over 2, these numbers keep getting bigger. Here we're going from pi over 2 to pi, so we're in the wrong quadrant now for these values. But when we were going between 0 and pi over 2, as we approached pi over 2, we were approaching 1 over 0, which is undefined, but 1 over just the tiniest little bit more than 0, 1 over 0.000000001. That's 1 over a tiny number, which is a huge number, right? So the closer you get to pi over 2, the bigger the values are going to get until you actually get to pi over 2, and there's no value associated with that. Now, this is more than your textbook shows you about this, but I wanted to show you why we had been learning how to plot polar coordinates. And the answer is that we sometimes get equations in polar form, and we need to know how to graph those. Sometimes you can take a polar equation and convert it into our Cartesian equation. In this case, we actually took a Cartesian equation and turned it into a polar equation. And then I showed you how to graph that polar equation. But take a look at the Cartesian equation. It's just a quadratic. It's not even shifted. It's stretched, right? This is just y equals x squared stretched with a factor of 4. So that's why this looks like a parabola. That's exactly what it is. And that's the connection. Polar coordinates are just a different way to find points. Now, was this overkill for this graph? Absolutely. But I did want to show you how to convert the equation and how we go about graphing polar equations. We're going to see a little bit more of this. In the next section, I'm going to show you how to convert a graph in an equation in polar form into an equation in rectangular form so that you can graph it.